So welcome back from the coffee break, everyone. This is a very special lecture now. So as you heard yesterday in Beate Spiegel's speech, there are very strong ties between the Heidelberg Laureate Forum and the Lindau Nobel Laureate meetings. And actually, the Lindau Nobel Laureate meetings were the model after which the Heidelberg Laureate Forum was designed. And so it's my great pleasure to welcome also Nicholas Turner from the Lindau Nobel Laureate meetings in the audience. So he is sitting in the back, but you can get a chance to talk to him afterwards if you want. And so for this year's Lindau lecture here at the Heidelberg Laureate Forum, it's a great pleasure to have Professor Reinhard Genzel. He is an astrophysicist and director of the Max Planck Institute for Extraterrestrial Physics. Professor Genzel received the Nobel Prize in Physics in 2020 for the discovery of a supermassive compact object at the center of our galaxy. And he will tell us about a 30-year journey, which probably has to do with his Nobel Prize, and it's my pleasure to welcome Professor Genzel on the stage. Welcome.
Well, it's truly an honor for me to speak in front of such exalted greatness in mathematics and computer science. So as you've heard, I'm just a simple-minded astronomer, an experimental astrophysicist, one should say. And the story I'll tell you about has to do with the fact that, as I will describe, 106 years ago, Albert Einstein introduced his new theory of general relativity, as you know, to describe gravity in regimes which had not been captured by Newton's theory. And as I will tell you, one of the results of this work was the prediction of objects which are rather weird, black holes. And it took 100 years to go from that theoretical prediction to a point where within the last, let's say, 1 or 2 decades for sure, in my case, 40 years, we've come from suspecting that these objects might exist to making them truly subjects of experimental study. Now that's something which, as you will see, you don't do by yourself. It's something which also takes time and perseverance. It has a lot to do with technology. Also, by the way, in computer science, very clearly, because we have very fast actions to do to read out detectors without generating any noise in the system, etc., to correct for the Earth's atmosphere and all these things. So this is teamwork. This is teamwork and really trying to push and push again and push further to do fairly difficult experiments. Now, as I said, black holes reach back, well, certainly to Albert Einstein, but actually already in the 18th century, one version of thinking about light, electromagnetic radiation at the time, was that those photons, so to speak, what we would now call photons, these corpuscles might actually see gravity. And if you accept that, and Laplace and Mitchell did that, if you accept that light sees gravity, then immediately it's pretty clear that if you make the object from which you send light elsewhere has very strong gravity, and light has a finite speed of propagation, then if gravity is strong enough, the light might not escape. So in a way, it's remarkable that these speculations by in particular Mitchell, already predicted black holes. But now, of course, as you know, it became then clear in the 19th century that the corpuscular theory of light was wrong, and that light was to be described as waves. And then, of course, this idea with gravity went away until Einstein brought it back up. So 1915, that was the time when he presented the theory. Already 1 year later, Karl Schwarzschild, there on the top, found the first solution for a spherical symmetric mass distribution, showing that indeed, if you have an object which has very strong gravity, such strong gravity, that the escape speed from the surface of that object becomes greater than the speed of light, well, then this object decouples in communication from the outside world. And vice versa, if you send a rocket inside of said event horizon, then actually all the mass and all the energy of the object is found at the very center, in a mathematical point for a non-rotating system. Now that prediction of the theory, many physicists believe to be wrong, because the theory is a classical theory and does not yet have the possibility to go to very, very small scales, where then the singularity predicted by general relativity might be smeared out. So we have to think about that in the future. The next 50 years, general relativity was mostly a mathematical subject. Roy Kerr, at the bottom right there, was the one to find the next characteristic of a black hole other than its mass, and that is its spin. Now there's a third characteristic with the electric charge, which won't play a role for those objects I'll talk about today, because in the astrophysical context, any charge will immediately trigger a current which would discharge the object. So astrophysical objects we would call black holes have two numbers, says general relativity: mass and spin. Now Penrose, who is in the middle there, with whom I had the honor to share the Nobel Prize, and Andrea Ghez, as you will see, as the third one, Roger Penrose showed that these predictions of Schwarzschild and Kerr were not owed to the very special geometries and symmetries assumed, that indeed formation of a black hole is a very natural phenomenon as long as the curvature of the gravitational potential exceeds a certain critical amount. Okay, so that's the 1960s, and indeed at that time the first possible objects in our universe were found which might be such objects. One were X-ray emitting double stars. X-ray astronomers at that time were able to look at the sky for the first time and found double stars with a bright star and a second non-radiating, not in the optical radiating second object, which however was a strong X-ray source. And indeed, we now know, and it was speculated then, that this invisible X-ray emitting object might be an accreting stellar black hole with masses which we now, I'll come back to this in a second, with masses between maybe a few solar masses to 100 solar masses. And then the next discovery was the discovery of quasars. Radio astronomers at that time also charted the skies, found objects which were not known before, very bright radio sources. And in the optical, they looked like stars, as you see here, fairly faint stars. Compact objects, fairly dim, not very spectacular, but highly variable. Some of them seem to emit a little bit of a puff of gas. Here, you see it here, which turned out to be relativistic plasma ejected from such quasars in form of a so-called jet. Now, when you look at the optical spectrum of these quasars, then you discover that whilst they're faint, they emit spectral lines in emission whose ratios in wavelength are very well known: hydrogen, helium, neon, etc., but all, in this particular case of one of the first quasars found, redshifted by quite a substantial amount, 16% for the first quasar in 1963. And Martin Schmidt, who used the Palomar telescope to make this measurement, then together with others, proposed that this shift, this red shift, was due to the expansion of the universe. And 16% redshift in terms of the expansion of the universe means that these quasars are far away. So in the 60s, more quasars were found, some at redshifts of several, such that what we're looking at are objects which are billions of light years away. We now know quasars, in fact, which are have been formed only a few 100 million years after the Big Bang. So that's remarkable. But are they? What are they? That was the question. How could you generate so much energy? Because if you convert the radiation you see, given the distance, you come up with thousands times or even 1 million times the radiation of the entire Milky Way, but now coming from a light year or something like this in diameter. How would you do that? Is that like in the Milky Way a bunch of stars? Very unlikely, very unlikely. And so here, a number of theorists, amongst them Martin Rees and Donald Lindau, whom you see here, but also Rashid Sanyaev and Roger Blandford and others, proposed the paradoxical explanation that what we are seeing in these quasars are highly, rapidly accreting massive black holes. And the idea is basically that before material, when it falls in, gas mostly, before it falls into the event horizon and disappears, you can convert up to, for a fast rotating black hole, several tens of % of the rest mass energy into radiation. Remarkable. About 1,000 times more efficient than fusion in stars. So that was the proposal. Next comes the question, well, we are scientists, right? So we need to prove such a hypothesis or disprove it before we can take it seriously. How can we prove that these quasars have a black hole at their centers? No, the answer immediately is pretty clear. Well, from gravity. If you could, like in the solar system, measure the motions of the gas, like the planets in the solar system, then you could, using gravity theory, measure the central mass. And if you come close enough, you could even say it might be a black hole. That's the idea. But quasars are so far away that this was technically not possible then. It's even nowadays just barely possible to make such spatially resolved dynamical measurements with big telescopes. Now, Lindau and Rees wrote a very interesting paper in 1971 saying, well, these quasars are very rare. And that's probably because we're looking at extremely highly accreting black holes. And that state might be rare. But perhaps, they said, not only a few, but many, maybe all galaxies have such a black hole at their centers. If so, well, then there might be such black holes also in the nearest galaxies to us, including our own. And then we have the resolution to look in their centers and make measurements. They thought mostly at that time about gas. In fact, the 21 centimeter line of hydrogen had just been discovered, and that was sort of the idea. Look at the center of our own Milky Way and measure the motions of gas and see whether there's a mass in the center. Now this kind of line of research, as you will see, then started off in the 1970s in several stages. And the Galactic Center became, over time, sort of the real best object to study this question because it's so close. Only 27,000 light years. Okay, so that's much, much closer. It's several tens of thousands times closer than the nearest quasar. So that's That's our laboratory. The Galactic Center is our laboratory. It stands, of course, for all the other galactic centers, and indeed other galactic centers are also being looked at. And so I'll tell you the story of these studies. Then the next big breakthrough happened, in fact, as you probably know, only a few years ago. The discovery of gravitational waves emitted from one of those X-ray binaries where two objects, in this case, two black holes, spiral into each other, and as they are very close, start emitting gravitational waves, and then disappear and form a more massive black hole. LIGO, the machine which has been used for this, is a marvel of modern technology. It also took those researchers about 50 years to get from the point of when they started to the triumph. Pretty much same time scale as it happened for the technique, which I will tell you. And then finally, photons themselves you could use, because photons, as Einstein theory says, sense gravity. And if you have photons come too close to a black hole, about 2 times the event horizon size, well then they will not be able to penetrate, so to speak, towards us, but fall into the black hole. So this technique requires extremely high angular resolution, which one can realize nowadays in short wavelength, millimeter radio astronomy. And as you may know, those radio astronomers have been successful in the last few years to image 2 such black holes, one of them being the Galactic Center, as you will see. So the Galactic Center is a disk galaxy, and as I said, we are in the outskirts of this system and not very far away, only 27,000 light years away. But as we fly here into the center of our Milky Way, there's a problem. And the problem is there are these dark spots and clouds. This is interstellar dust, which in fact diminishes optical light by about a factor of 10 to the 12. So that we have to go to longer wavelength to look into the center of our Milky Way. Nowadays we can do this with modern technology, as you will see. You can also look at radio waves, or you could use it X-rays, but you cannot see the galactic center in the optical. Now when you do so and look in the central few light years, as you see here, you find in blue a very dense cluster of stars, about 1 million times denser than the local universe in our neighborhood of the sun. 1 million times denser. And at the center of that dense stellar cluster, this nuclear cluster, is a compact radio source, which we now call Sagittarius A star. And the radio astronomers have measured with this technique of interferometry that the diameter of that source is a mere 40, 50 microarc seconds, depending on the wavelength. 40 microarc seconds is about 10, 20 centimeters on the moon. So it's a very compact object. In fact, fits the bill of, if this were a black hole, of a few million solar mass black hole in terms of the size of the environment of the event horizon. Now you see also, in addition, extended structures in pink and green. These are interstellar dust clouds which have been found in the very center. And you can use the Doppler motions of these dust clouds, to measure the motions, and thereby have a tool for measuring gravity, like I described earlier. In the 1970s, Nobel laureate Charles Townes, who had gotten the prize for the invention of the maser and the laser, had moved from MIT westward to Berkeley, California, and he knew how to build equipment, in the spectroscopic equipment in the infrared. And he and his students, and I then joined as a postdoc and then also professor in Berkeley, we looked at the central region here and measured the motions of these gas clouds in spectroscopy, in the Doppler motions. And as you see in the bottom right there, from this we could deduce something about the distribution of mass. So when you look at this region here, then on the horizontal scale is the distance from the center of Sag A star in logarithmic units. And on the vertical scale, also in logarithmic units, is the mass. So when you go from large scales in the upper right towards the center, the mass decreases. And that tells you there is an extended mass, and that is the stars. That's the nuclear stars. But then when you go inward, at some point, about a few light years from the center of Sag A star, all of a sudden the mass does not diminish any further. Seems to be approximately constant. So Towns and the Berkeley group were convinced, oh, there's a black hole there. A black hole of a few million solar masses. And we wrote a Nature paper. But nobody believed us. Why not? Well, first of all, the concern was that clouds, interstellar gas clouds, may be a relatively poor way of measuring gravity because it can be pushed around by forces other than gravity. So, for instance, magnetic fields or winds from other stars. So it would be better to use the stars, in fact. That was clear, but that we couldn't do at the time. And the next problem is this measurement of a few light years is 1 million times the event horizon of a few million solar mass black hole. Boy, everyone said, maybe a black hole, but it could also be a cluster of faint stars, a cluster of neutron stars, which also had been discovered at the same time, which are bunched towards the center, but are not in a configuration of a black hole. So the evidence is interesting, tentative, but it's not convincing. So this is where technology comes in, and let me just describe a little bit of that. So in the infrared, of course, at that time, we had very poor detectors, certainly no imaging detectors. The American military had it for obvious reasons of being interested in Russian rockets. But then over time, it became possible to take this technology and bring it into the civil sector and even to Europe and basically build up what we now have, namely very large imaging detectors with very low noise. So we have cameras which allow us to image infrared waves. The next problem is the atmosphere. So if you take a telescope on the ground and look at a distant star or galaxy, then the waves have to go through this turbulent refractive atmosphere, basically getting distorted, and of course, because of the winds, move around. So the images are unsharp, independent of the size of the telescope. Well, to correct for this, you have to first sense how much are the waves distorted, and then with a deformable mirror in the path of the optics, you can, at least theoretically, undo what the Earth's atmosphere has done. So that technique, adaptive optics, was moved forward in the 1980s, 1990s, and is now our standard technique. With that technique, you get to the diffraction limit, the ultimate limit of a telescope. And so also in the 1990s, 2000s, the next generation of bigger telescopes became available. Before that time, there were typically 3-meter class telescopes. But then nowadays, we have 10-meter class telescopes. And with adaptive optics, you can then go from this smeared out, seeing limited thing to truly diffraction limited imagery, which is typically 20 times better than what the atmosphere otherwise allows. And it's without limit. So we are currently building now in southern Chile the next generation telescope of the European Southern Observatory, which will be a 40-meter telescope. So still another factor of 4 to 5 bigger than telescopes we had in the past. So it's these techniques which give us the possibility to make very sharp images. Finally, to make these corrections I discussed, you need a fairly bright star to analyze the wavefront. in very short time, because the coherence time of the atmosphere is typically only a millisecond or a few milliseconds. Well, that brightness of a star is rare. But, and that's the next technique, you can make your star. So we've learned to use the lasers, which we shoot up into the upper atmosphere, where it's known through LiDAR measurements that meteorites, which come into the Earth's atmosphere from time to time, get destroyed, and a little rain is coming down, which has in it sodium. So we take the lasers to the sodium D line and shoot that up in the atmosphere to 90 kilometers, focus it there, and use resonant backscattering to then generate an artificial star which goes back through the atmosphere and produces a possibility to make the correction. So you see quite a bit of technology and more, as you will see in a few slides, in order to get to the goal. And then in the 1990s, we, using the telescopes of the European Southern Observatory, and my colleague Andrea Guess and her colleagues using the Keck telescope in Mauna Kea, were able to then look at the motions of stars, patiently taking pictures every year and see whether the stars would move. And here you see images from 3 different years in red, in green, and in blue. The cross in the center is the position of Sagittarius star, and the circle is about 1 light month. So you can see that red, green, and blue means that something moves. So there are stars close to Sagittarius A star on this image which move with a few thousand kilometers per second. That's tremendous. That's, very, very much faster than the Earth around the Sun. And that on scales now of light weeks. And indeed, the result of these measurements, which we had in the mid and end 90s, and both groups agreed, was that indeed there was a few million solar mass object, as we had thought a decade earlier. But now we had it with stars, and now we had it on a much smaller scale. So the astronomers were beginning to believe us that there might be an object in there which might be a black hole. The physicists didn't. Physicists were more skeptical. They said, well, okay, it's consistent with the black hole, but does it have to be one? Could it not be some other configuration? So back to the drawing board. What do we need to make still better measurements? Bigger telescope. Well, that was not possible at that time. But if you happen to have a star which comes closer to the center, well, then that would do the trick. That was deemed to be unlikely, but it happened. We found stars, indeed, which, basically would come close to the center. And pretty soon thereafter, Keck measurements of Andreas showed that you could see not only the motions, but also actually accelerations, curvature. So there was the chance, maybe, over time, to see an orbit. And that's a very, very precise way of measuring the gravitational potential. And we were lucky that there was one star, S2 we call it, which in 2002 moved to a distance of only 17 light hours away from the galactic center. Had a motion of about 2.5% the speed of light at that point, and is on a highly elliptical orbit. So now you can measure the mass again. It's again the same number, but now we are on scales of about 1,000 times the event horizon of a few million solar mass black hole. There's very little you could now think might be pushed in there other than a black hole. So over time, we were able to measure the motions of this star very, very precisely. This star, at its peri distance, as you see on the right side there, is only about 3-4 times the size of the solar system. So we're really on very small scales. And the orbit is directed in a way that as we look at it, it moves towards us. Okay, so we can actually measure the three-dimensional structure of this orbit. And not only of that orbit, both groups over the next 10 years were able to see about 50 stars all moving in the central region. By the way, this physics story I'm giving you is only part, of course, of the astrophysics story, which is involved in all of this, which is, heck, how did these stars get in there? Very unlikely. Every peer review committee would have said, no, there can't be any stars in the center. Okay, we were naive enough to just go ahead and build the instrument and measure it, and sure enough, there are stars. And they can be used as very precise tools. Next. What is next? Well, we can build a bigger telescope by combining the light of the 4 telescopes on Paranal in Chile, each of which is 8 meters in size. And these 4 telescopes of the ESO VLT are placed, as you see, from each other to a distance of about 150 meters. So if you can go ahead and then bring the light from coming from the galactic center through a tunnel system precisely aligned into a combination system, carefully measuring all the distances and so forth to about 10 nanometers, then you can combine the light and basically turn this into a virtual telescope of 130 meters in diameter. That's another factor of 20 in resolution. And this experiment, which we call gravity, led by Frank Eisenhower, took us and ESO about a decade to build, and then we had it right in time for the star S2 to come again. Because this S2 star has a period which remarkably is only 16 years. 2002 plus 16 is 2018. So here we are, we were on time to see the star coming in for its second peri approach. And now we could measure with extremely high precision. The measurements with adaptive optics are in red, the one with the interferometry in blue. Very, very precise measurements. At Peri, which was in May 2018, we could see the motions from night to night. And the star was moving at about 7,500 kilometers per second. In addition, of course, we do measure also the Doppler shift of the motion along the line of sight through spectral lines. So we have all 6 phase space coordinates to fit now for the orbital parameters of the star and also the central mass and the distance to the galactic center and various nuisance parameters. And we can check general relativity, because to predict that there's a black hole requires that general relativity is actually applicable in this regime where it's never been tested with very, very large masses, etc. The first such effect which general relativity predicts is the so-called gravitational redshift. So if you have a star moving very close to a central mass, sending light to us, then as it escapes from the potential well, it is shifted due to time dilation, if you like. And this shift you can measure in the spectral lines of the star. So if you subtract from the data we receive the Newton orbit, which then shows up here as a horizontal line, general relativity predicts this red line, which is different from this by only one part in a few parts in 10 to the minus 4. And that's the measurement. So you clearly see, you confirm the expected redshift of gravitation. The next effect is, while in Newton, if you have a planet or a star orbiting another star and nothing else is around there, the orbit of such a bound object stays put in space. Not so in general relativity. In general relativity, it precesses. It precesses in the plane of the orbit, and that's the so-called Schwarzschild precession. And if the central object has a spin, is a black hole with a spin, then there's also a second precession around the spin of the black hole. Now, we can actually see this minutiae effect of Schwarzschild precession. See, in 2005, the orbit was there in 2021, it's shifted a little bit to the right. Or if you put this into an angle and subtract again Newton, you can see that 16 years ago we were up here, and then all of a sudden the orbit made a kink and is now moving just as general relativity predicts. We have not been able yet to see the so-called lens steering precession due to the spin. That's another factor of 30 more difficult to do, but of course we are intent to do. We also can test the so-called equivalence principle. The equivalence principle, in form of its local positional invariance, states that two falling objects have the same properties as far as gravity is concerned, independent of their composition. And we can actually mimic this experiment by using in the star the spectra due to helium and hydrogen, which you see there, and measure the orbit in these two species independently. And we can then fit for this nuisance parameter beta, which according to general relativity should be 0. And indeed, it's fairly close to 0. So GR is pretty good. But we are still 1,000 times away from the event horizon. So you could say, how sure are you that there couldn't be anything else? Well, actually, we can now get closer to the event horizon because from time to time, every few days, the black hole itself emits intense radiation in the infrared. We call those flares. They last for typically a few hours. And when we do that with the interferometry experiment, we can then measure the motion of the centroid of the emission around the position of the black hole. And they loop on a loop of a few times the event horizon size in about 30, 40 minutes. So it looks, and that with a speed of about 30% the speed of light. So that does look like what you would expect for motions of gas around a very compact object. Likewise, there is this gas is polarized because it's synchrotron emitting electrons, so we can measure the polarization of the light. We can see that swings around also on the same time scale because this region around the event horizon is highly magnetized due to strong magnetic fields, which you see in this image. And then finally, the experiment the radio astronomers can do, namely to look in the direction of the black hole and look at radiation which comes from the backside here. And the prediction of general relativity is that everything within 2 times the event horizon size is bent inwards and does not reach the observer. And indeed, that's what our colleagues published a few months ago. And indeed, this size here is given by the ratio of the mass and the distance, both of which we know from the stellar orbits to a fraction of a percent. And indeed, the circle there is 50 microarcseconds, indeed, as predicted by our tests. So 40 years after we started, we've moved inwards from distances of a few light years from the central mass, ever better, with ever better precision. Our colleagues from UCLA did the same, found the same, and so we can measure on a scale of about 1,000 times the event horizon, the mass and the distance to a fraction of a percent, as I said. Highly precise laboratory type measurements. But there could still be something inside. There could be, for instance, dark matter. If there were heavy dark matter particles, in principle, you could imagine a configuration in the compact central region. But what I just shown you from the flares and the radio emission size tells us, no, that's not possible, because the same mass which we measured with the stars is also at about 3-4 times the event horizon size. So that fits together. This thing is a black hole. Is it a black hole as predicted by general relativity? Well, for that we need to measure the spin. We need to measure the spin because we still don't know, so to speak, is it following the Kerr metric, as we would say. It fits, it's consistent with, But it could be a Schwarzschild black hole, for instance, without a spin. This we still have to do. Now, let me at the end briefly say, cosmologically, we also have learned in the meantime, through many, many measurements, that these black holes indeed are common, that all massive galaxies had them, that the evolution over cosmic time of the galaxies and the evolution and growth of black holes are intimately coupled. Material which falls into the galaxies and make them grow trickles down and makes the black holes grow. And in fact, when the black holes are accreting from time to time a lot of material, they also spew out, like quasars, radiation and winds, which in fact affect the galaxy. So there is a symbiotic relationship, which in fact we now know means that galaxies cannot apparently grow more massive than about 1.5 times, 2 times the mass of the Milky Way. Because the black holes, if you feed them just enough, start dispersing the gas. And the growth over cosmic time, indeed, are coupled. So we are here 13.7 billion years after the Big Bang. The first galaxies started growing a few 100 million years. And grossly speaking, the star formation rate in galaxies and the quasar density follow the same path. So this is this co-evolution of these two systems. Now we hope to learn more, of course, about the earliest times. When did the first galaxies form? And what mass were the first black holes? That's something which we need to check out in the next decades to come. Finally, are these really Kerr holes? And does the so-called no-hair theorem apply? Because general relativity, as I mentioned in the beginning, predicts that black holes have only 2 numbers, a mass and a spin. No hills, no complex surfaces, just 2 numbers, apart from the charge. Can we prove that? And the answer is, I think there is a chance through gravitational waves. In about 15 years from now, the European Space Agency, ESA, is planning to launch a very ambitious space experiment called LISA, which will be 3 satellites 2.5 million kilometers away from each other, measuring with lasers very precisely the space-time variations between them. And if a distant massive black hole orbits another distant massive black hole or something like this, then these variations could be measured very, very precisely. In particular, if a stellar black hole spirals into a massive black hole, then you could hear that. And if you measure this with LISA, well, here I come to my technical inability to get at my sound. But basically what you would hear is a humming of this system, and as gravitational radiation is emitted, that humming goes to higher and higher frequency until finally the 2 systems spiral in together. And all of this here in the very end can test general relativity extremely precisely. This is also an extremely difficult experiment. I won't probably be there to see it, but it's going to be highly exciting. And in fact, this is one at the forefront of modern physics, which many people are very much interested in. Thank you very much.
Thank you very, very much for taking us onto this very interesting journey from the past, but also into the future. So this was very, very interesting. I think we have time for just one short question. So there was one first hand up there.
Hi, Professor. It was really fascinating talk. My question is, my background is computer science. I was wondering, do you see any scope where the computer scientists can help you, like in your research as an astrophysicist? So I come from University of Always, really close to Arctic, and there we have been working on how to build a network which transport massive amount of scientific data from Arctic to the researchers' laboratory all the way, in the mainland.
The answer is, of course. Without you guys, we couldn't work. As simple as that. Astronomy has, in many ways, always been one of the first customers of ever more powerful computers. In one way, this data here, which you see in front of you, if you have LISA in space, there are hundreds of objects which will hum at the same time. And to sift out that mess of noise and model it will require the most sophisticated computers. Likewise, astronomy is trying to understand the evolution of the universe, of course, in physics terms, but the universe is very complicated. So the tools we're using are simulations. And simulations require the biggest supercomputers possible. We have one in Garching, and our neighboring institute is using this supercomputer for more or less the entire year to calculate the evolution of the universe. The answer is yes. And as we look at distant galaxies like the James Webb Telescope does now, we require, in order to understand what we're seeing there, big data analysis facilities which are not thinkable without most powerful computing facilities.
Well, so, sorry, we don't have more time for more questions, but Professor Genzel is around, so you can approach him also later in the lunch break to talk to him. So thank you very much for this very, very interesting journey.